Okay, so welcome everybody to the DTP Colloquium. It's a great pleasure to have Toru Kojo from Tohoku University, and he's going to tell us about sound velocity peak as a signature of quark matter powers. Toru, please take it.
Okay, so first of all, thank you very much for the invitation. And it's a great pleasure to give a colloquium at Tata Institute of Fundamental Research. So actually, I've never been to India, but actually, this is my third time to give a colloquium at the Institute of India through online. So anyway, so I'm going to speak about equation state of neutron star matter from a QCD perspective. So in particular, I will address the question of what differentiates nuclear matter from quark matter, and what should be the signature of quark matter formation. And my answer will be the sound velocity peak. So that characterizes rapid stiffening of matter from nuclear matter to quark matter. So especially, I will emphasize the quark substructure of hadrons are crucial to explain this rapid stiffening. So that will be my main conclusion. But I had that there are broad audience in this colloquium. So therefore, let me briefly remind you what is QCD, and let me briefly explain what is the current status of dense QCD in schematic manner. And then I will discuss neutron star structure and recent constraints on equation state. Then I will start to discuss sound velocity, and I will give some orientation using the purely nuclear matter and purely quark matter. Then this first part is my main statement. It includes my main statement. I will discuss the description which cover from low density nuclear matter to high density quark matter in unified manner in using the single degrees of freedom. And actually, for this description, so I will describe one physics using the two different languages. One is based on quarks and one is based on the baryon, and we can freely change the language, and then I can look at this system from the several perspectives. And then I will apply this description to the famous hyperon puzzle, which is a critical issue for the conventional nuclear physics. Okay, so let me briefly mention, let me give a few words on QCD. So QCD is, of course, the theory of strong interaction. The basic degrees of freedom are quark, anti-quark, and gluon. And gluon has a charge. And these gluons are a charged object. And at this point, the theory is very different from the quantum electrodynamics, in which gauge bosons are photon, which is a charged neutron. So when we go from classical theory to quantum theory, the difference becomes significant. So in the case of QED, when include quantum correction for the electric force between electron and positron, then photons are screened, and the force becomes weaker and weaker at longer and longer distance. In contrast, in the case of QCD, there are also the quark and anti-quark screening for gluon, but there are anti-screening because gluons have a color charge, and charged object can couple to gauge boson. That means gluon can couple to another gluon and another gluon, etc., etc. That produce anti-screening effect. Therefore, at longer and longer distance, interaction becomes stronger and stronger. And for shorter and shorter distance, interaction becomes weaker and weaker. This is a celebrated asymptotic freedom. And this stronger interaction in the infrared produce two distinct phenomena in QCD. The first one is a famous color confinement. So if we place a charged object like this, if we place a source and sink, then from the source, it generates the electric field. In the case of QED, electrodynamics, this electric field is widely spread out over the space. But in the case of QCD, quark create a color electric flux that is strongly squeezed due to quantum fluctuation. Due to quantum fluctuation. Just a second. Okay. Due to a strong quantum fluctuation. And then there are no leakage of the color electric flux. So there are colored quark and colored anti-quark that is connected by a color string. But as a whole, there are no color leaked out. So this is color confinement. Another important phenomenon in QCD is chiral symmetry breaking, in which quark and anti-quark make a pair. So usually, creating a quark and anti-quark cost energy of the order of mass. But if there are a strong attractive interaction between quark and anti-quark, then system favor the quark and the anti-quark pair, which is kept excited because of this attractive energy. And then when the number of this pair becomes macroscopic, then the structure of vacuum change, and then quark acquire the mass gap, effective mass, so-called constant quark mass of order 300 MeV. So these two phenomena gives us a picture of hadron physics. So first, chiral symmetry breaking generate a mass for each quark, and each quark are trapped into a single object in a color white or color singlet way. And then the baryon baryons are made of 3 constant quark, and its mass is order 3 times constant quark mass, that is order 1 GeV. For meson, we create a color singlet object by combining quark and anti-quark, and its mass is typically twice constant quark mass. So these are called ordinary hadron. And in addition, there are Goldstone boson associated with chiral symmetry breaking. And so these ordinary hadron, together with Nambu-Goldstone boson, form the basic picture of hadron physics. So these are basic degrees of freedom. So as I said, so strong interaction in the infrared gives a constant quark mass to the ordinary current quark, and the quark acquire the mass of order 300 MeV, mass of order 300 MeV. And at even a longer distance, these constant quarks are trapped into a color singlet object due to color confinement. And then it forms a nucleon, such as protons and neutrons. And these nucleons interact through nuclear forces, and then create the various nucleus and also a nuclear matter. In the context of the universe, and in the early stage of the universe, we have a quark-gluon plasma in which hadrons are totally overlap, and we observe its constituent, quarks and gluons. After the universe cooled down, various galactic structure as well as neutron stars are formed. And this is the neutron stars is the object which I would like to discuss today, where nuclear and the quark matter are inside. Okay, so this discussion motivates us to consider the so-called QCD phase diagram. So this is a temperature axis. This is a high temperature region. And there are also baryon chemical potential. Roughly speaking, it coincides with the high density domain. So there are 3 distinct regions. So at low temperature and low baryon density, we have a hadronic matter, where basic degrees of hadrons. But if you heat up this hadronic matter, then hadronic matter continuously transform into a quark-gluon plasma. And also, degrees of freedom look totally different. So hadronic matter, hadron basic degrees of freedom, and quark-gluon plasma, we have a quark and gluon. So also degrees of freedom look very different. Actually, this transition is not discontinuous, but it is just a crossover. Okay, it is not first order nor second order, but it is a crossover. And this quark-gluon plasma is studied through the relativistic heavy ion collision, as well as lattice QCD simulation, as well as the effective model. And this field is now mature. Okay, so the study of this object is now reaches a sophisticated level. And another important physics can be found at low temperature and high baryon density, in which the physics contain the physics of neutron star. And this field is actually quite old. It started last century from 1930. And there are still a lot of uncertainty to understand this domain. But last about 20 years or 10 years, so this field is now rapidly developing thanks to the advancement in the observation. In particular, in 2019, so there was a discovery of a gravitational wave from a neutron star merger or neutron star collision that emit a gravitational wave. And in addition to a gravitational wave, there are also electromagnetic signal and also neutrino. And in that sense, there are a multi-messenger. Therefore, this field is called now a multi-messenger astronomy, which has just begun. So in today's talk, I will mainly focus on the property of a neutron star, emphasizing the picture, the viewpoint of QCD. Okay, so now what is the fundamental problem and question in dense QCD? So there are several conceptual questions first. So first question is about what is the nature of confinement-deconfinement phase transition. The second question is the fate of quark mass. So usual study or conventional modeling suggests that so at higher and higher density or very high temperature, the chiral restoration or chiral symmetry should be restored in the extreme environment. And if this is the case, so we have to address the question, so what would happen for the constant quark mass? So this must vanish. If this must vanish, then there should be something radical. Something radical should happen. And the third question is, so what can distinguish the nuclear matter and the quark matter? So how they are related? So the more concrete question is whether this transition can be separated by order and order transition, or it can be connected smoothly by a crossover, as in finite temperature QCD. And the fourth question is, so theoretically, we can imagine quark matter can exist, but whether it can be realized in the universe or inside the neutron stars are a very different question. And this is actually the hot topic in our field. Okay. Sorry,
Is there any question from the audience?
Yeah, please.
Okay, I guess not. Sorry, please go.
Okay. Okay. So as I said, the physics of neutron star has a long history, but it has not been fully understood. And there are, of course, some difficulty. And let me briefly summarize the difficulties. So first and perhaps the most important difficulty is, so there is no first principle calculation available. In particular, lattice Monte Carlo simulation cannot be performed at the finite density because of the previous sign problem. The situation is quite different from a hot QCD case, where lattice QCD simulation gives us the lot of crucial information. But we cannot ask help from lattice QCD for finite density. Then another problem is we cannot design the dense matter system, or we cannot prepare a laboratory, but we have to wait for signal from the universe. So we cannot control the such a dense. We cannot create such a dense and cold matter from the laboratory experiments. So, for example, the heavy ion collision. Okay. So we can create a compressed matter, but that also produces a large heat. So therefore, matter must be hot, and therefore it is not cold matter. And so it is difficult to keep such cold matter for a long time. And this is not possible for by the heavy ion collision. But we have to look for some object in the universe. So this situation is again different from the heavy ion collision or hot QC. And the third difficulty is actually conceptual. So nuclear matter itself is theoretically very complicated system. So first, its interaction is very strong. And there are also some conceptual subtlety. For example, when we consider a nuclear matter or nuclear many-body system, then we have a nucleon, and they interact through the meson exchange at long distance. So pion, low meson, or omega mesons are exchanged between nucleons, and that creates strong forces. But if we look at this interaction in more microscopic way, then this meson exchange is just a quark exchange. Okay, but this quark is connected in the color singlet way. But if you go to denser and denser system, then color exchange in nuclear domain and quark exchange in high density regime. Actually, it is not clear whether this is some transition between these two descriptions. So therefore, actually, the distinction between nuclear matter and quark matter is actually not easy at all conceptually. Okay, so now, so this is the picture which has been developed by last 10 years, in the last 10 years. So this sort of description was started by Masuda Hasa Takatsuka. So they created a first practical crossover modeling from the nuclear matter to quark matter. So there are 3 or 4 distinct regimes. So at low density, of course, we have nuclear matter, where nucleons interact through meson exchange or quark exchange. And since our system is dilute enough, the nucleons are well-defined object, and the nuclear matter description should be just conceptually fine, even though the calculations are difficult. But this regime, so this situation change beyond the twice nuclear saturation density, where it is known that the many body forces are important. So this is 2 body forces, but this is 3 body forces. So 3 nucleons are interact at once. So this importance of many body forces indicate there are many quark exchange among baryons. And if this is the case, it is natural to expect the structural change of hadrons, baryons, as well as the excitation other than nucleons, such as hyperons, delta, etc., etc. And in fact, this regime is theoretically more difficult because degrees of freedom are not clear-cut, as you can see from here. On the other hand, this regime is most important in the context of neutron star physics. So I will come back to this point later. But let us go beyond 5 times nuclear saturation density, even higher density. Then our description becomes actually simpler after baryons overlap. So after baryons overlap, so natural degrees of freedom become quarks. And in that sense, we can regard this matter as quark matter. However, this quark matter should be distinguished from the conventional ordinary quark matter, weakly coupled quark matter, because there are perturbative QCD calculation which predict the breakdown of weak coupling expansion at density less than 40 times nuclear saturation density. By the way, nuclear saturation density is the density of a nucleus, typical density of nuclear. So since perturbative QCD predicts its weak breakdown weak coupling expansion at density less than 40 times saturation density, so in this domain, although natural degrees of freedom look quarks, but this matter must be strongly correlated. So therefore, this matter should be regarded as strongly correlated quark matter for the domain between 5 to 40 times nuclear saturation density. And this regime has not been studied in detail. But in what follows, in today's talk, so I will mainly focus on the physics between 2 and 5 times nuclear saturation density using the hints from neutron star physics. Okay, so now let me move to the topic of neutron star structure and the recent constraints on the equation state. So a neutron star is actually a very rapidly rotating star, which is extremely compact. So its mass is about 1 to 2 solar mass. Okay, it's heavy, but its radius is only about 10 to 12 kilometer. Okay, which is 10 to minus 6 times smaller than the sun. Okay, so it's extremely compact object, and the temperature is extremely low, the order of kilo electron volt. So this dense object, so is okay because we have a large energy density within very small domain. The gravitational fields are very strong, and therefore we have to describe neutron star using general relativity. That is first important point. And another important point is, so since we roughly know the mass and radius, so you can estimate the density inside of a neutron star, and the density is order 0.1 to 1 inverse cubic Fermi. And this is coincides with the typical scale of QCD. So it is clear nuclear matter or quark matter should be important inside of a neutron star. The most basic quantity in neutron star physics is the mass-radius relation of a neutron star. And it can be calculated by solving Einstein equation coupled to a QCD energy momentum tensor or QCD equation state. And what is crucial is the balance between energy density and pressure. So when energy density is large, and then it creates a large storm of gravity that try to compress a material in this way. But if you compress matter, then pressure increase inside, and then that resists to that gravitational force. But if this increase of pressure is too small, then gravity wins, and a star gravitational collapse to the black hole. So what is important? What is important is to compare the pressure and energy density. So now we introduce terminology soft and stiff. So this is pressure versus energy density. And when we call the equation of state is soft, that means at given energy density, pressure is small. For such a soft equation of state, the neutron star tend to have a small radius and the small maximum mass. If equation of state is stiff, in that case, a neutron star has a larger radius and larger maximum mass. But what recent neutron star observation seem to suggest is QCD equation of state seems to be the soft to stiff type. That means equation of state is soft at low density, but very stiff at high density. And in that combination, neutron star tend to be compact. Nevertheless, maximum mass is high, beyond 2 solar mass. Okay, so before going further, let me briefly mention some history. So where are we now? So the neutron star itself has been predicted by Zwicky and Bade just after the discovery of neutron by Chadwick. And after 30 years, so this just after 30 years, so this prediction was confirmed by Bell and Hewish by the discovery of pulsar. So pulsar is very rapidly rotating, and to prevent material stripped out, so radius must be compact because surface velocity must be smaller than the light velocity, and also to avoid matter flying away, the gravitational force must be sufficiently strong to maintain such compact object. So that confirmed the existence of neutron star. And soon later, Taylor and Hulse discovered a binary pulsar. So that is double neutron star object. And from the decay of orbital period, decay of orbital period just coincide with the prediction of general relativity. And actually, this was a confirmation of indirect confirmation of existence of gravitational wave. But what was revolutionary in last 20 years is a discovery. That revolutionary discovery start around 2010 through the discovery of 2 solar mass neutron star. So this gave us a new guide or new guideline for the understanding of high density equation of state. So equation of state must be very stiff to pass this two solar mass constraint. So that is the first revolutionary discovery. And another revolutionary discovery is any question? So there is some noise. So is it okay to continue?
Yeah, please continue.
Okay. So another revolutionary discovery is a discovery of a gravitational wave from neutron star merger, together with some electromagnetic counterparts. So this discovery opened a new field called the multi-messenger astronomy, which utilizes the gravitational wave signal, electromagnetic signal, and also neutrino. Although neutrino has not been discovered so far. Okay. So now let me go back to the discussion of mass radius relation. So this is a typical mass radius relation you can find from the literature. So let me begin with the low mass region. And let's consider the star of having the radius of 20 kilometers. That is actually a theoretical object. So the structure is the following. So we have some core, which is rather dense, and we have some crust, loosely bound crust around the core. And since the neutron stars are not so heavy, the gravitational attraction is not so strong. Therefore, the loosely bound object is now widely spread out. So that's the reason why our radius is very large. Okay. But if you look at a slightly heavier object, then gravitational force is a little bit stronger. Okay, but a little bit stronger gravitational force is enough to compress this loosely bound material. Okay, so therefore crust radically shrink. Therefore, radius becomes radially smaller, considerably smaller within small increase of the mass. But if you continue this discussion, then eventually a crust becomes very, very thin, and we start to observe the radius of the core. Okay, then this mass radius curve start to go up because we can no longer easily compress matter. Here we have some stiff matter, which that prevent the further shrinking by the hard core, for example. Therefore, radius no longer change radically, but the mass simply goes up as we increase the density at the core. And there might be hadronic matter or quark matter at higher density, or there might be first order Ferris transition. Okay, but what mass radius relation must satisfy is the maximum mass constraint. So since 2.08 solar mass neutron star has been discovered, so any realistic equation of state must pass this constraint. Namely, mass radius relation can go beyond 0.8 solar mass. Otherwise, if the equation of state that cannot pass this constraint must be rejected. Okay, so this is the basic structure of mass radius curve. And so historically, so this two solar mass constraint plays a very important role to reject the unrealistic equation of state. But actually, this two solar mass constraint itself is not powerful enough. So if we allow a neutron star with very large radius, then it is not so difficult to pass a two solar mass constraint. Especially even when we are imagining some first order phase transition that soften equation of state radically, we can still pass a two solar mass constraint. So if we start with very stiff equation of state, so even after the first order phase transition, which involves the shrinking of the radius, we can still pass a two solar mass constraint in this way. Okay, so from this argument, so to understand the phase structure of QCD, okay, so this first order phase transition characterizes a distinction between the hadronic matter and the quark matter. Okay, and if this scenario is possible, there are some first order phase transition between hadronic matter and the quark matter. Okay, but if radius is smaller, then a first order phase transition including a softening of the equation state, cannot pass the two-cell mass constraint. Okay, so therefore, from this argument, it should be clear that radius should be very important. Okay, radius constraint should be very important. So that was a situation about 5 years ago. But nowadays, so we can also find the constraint on the radius. The most up-to-date constraint came from the NICE's analysis. So actually, NICE studies the X-ray from some pulsar, but they also include other constraints from the other discovery. So this is actually a summary plot, including all constraints which have been available. Okay, so the NICE studies the mass radius relation for the massive neutron star, which has a mass of 2.08 solar mass. And they estimated that radius to be 12.4 kilometers. So they also took into account the constraint from a gravitational wave event, GW170817, as well as their study of X-ray pulsar. And they found the 1.4 solar mass neutron star should be somewhere around 12.5 kilometers. And they also took into account the low density nuclear constraint, which is based on a nuclear experience and also first principle calculation. And including all these constraints, so they conclude the 1.4 solar mass neutron star and 2.1 solar mass neutron star has a similar radius. Okay, so curve just rather so the radius doesn't change much from 1.4 solar mass neutron star and 2.1 solar mass neutron star. So this information is pretty important. So for example, if we had the first order phase transition between 1.4 and 2.1 solar mass region, that corresponds to the density, roughly speaking, the density around twice nuclear saturation density to 5 times nuclear saturation density. But in that density domain, so radius doesn't change. So if there are, for example, a strong first order phase transition like this, so during first order phase transition, pressure is constant, but energy density or number density jump. Okay, so this means a radical softening. And if this had happened, then the radius should radically shrink like this. Okay, but this sort of behavior has not been found so far. So therefore, this comparison between 1.4 and 2.1 solar mass neutron stars radius suggests there should not be strong first order phase transition. Okay, so this is the reason why we will consider equation of state to be a soft to stiff type. But theoretically speaking, this soft to stiff combination is quite challenging because of the causality constraint. So the soft to stiff combination means that the equation pressure is small at low density, but it must reach a stiff equation state at high density. And in between, there must be a rapid growth of the pressure as a function of energy density. Okay, so this is a soft to stiff combination. But this slope, dpd epsilon, is nothing but the square of the sound velocity. And since this is velocity, it must be smaller than the light velocity square. Okay, so in this way, the low density domain and high density domain, or nuclear physics or quark matter physics, constrain each other through the causality constraint. So for example, so if we had a strong first order phase transition like this, okay, then the pressure is constant, energy density jump. And in order to pass two solar mass constraint, we have to have very rapid growth of the pressure, but it would violate the causality constraint. So in order to avoid this sort of problem, the simplest and the most natural way to connect the soft region and the stiff region is to just consider the smooth curve, okay, without much structure. And this observation led us to the picture of quark-hadron continuity as our baseline. Okay, and of course, this argument itself does not fully reject weak first-order phase transition. But as far as phase transition is weak, we can treat such a small phase transition as just a perturbation to this smooth baseline. And this is our strategy anyway. Okay, and as I said, so equation of state should be soft to stiff type. So the sound velocity is initially small, but it must becomes larger. And then eventually it has to go to the so-called conformal limit when kinetic energy dominates over the interaction energy. So this must be the consequence in the non-relativistic limit. And in between 2 and 5 times nuclear saturation density, this slope is the largest, and it makes a peak. Good. So this is a conclusion derived from low density constraint, high density constraint. But on the other hand, we also want to know what is the microscopic origin of this sound velocity peak. So there must be some physics related to this existence of sound velocity peak. So the last half of today's talk is about the microscopic origin of this peak structure. By the way, if we just consider the purely nucleonic description, then sound velocity does not make a peak like this, but it gently grows like this. Okay, so stiffening occurs at higher density in the case of a purely nucleonic description, and that leaves some consequence on the mass radius relation. Okay, so although for 3-color QCD, it is not fully established whether sound velocity peak exists or not. Okay, so there are some other arguments also, but the first question is whether sound velocity peak is possible and whether sound velocity can exceed the conformal limit. I'm saying this because some people claim that sound velocity should not go beyond the so-called conformal limit. The sound velocity square equal to 1/3. So this is basically a relativistic limit. So some people claim the sound velocity should not exceed this bound. And so there has been some issue, but recently, although 3-color QCD is cannot be studied by lattice Monte Carlo simulation, but there are some theory, QCD-like theories, such as so-called 2-color QCD or isospin QCD, for which lattice Monte Carlo simulations are possible. And this theory can be used for the proof of the principle. And the discovery is the following. So for 2-color QCD, Ito and Ida first discovered the sound velocity peak like this. And recently, there are also studies for the isospin QCD, and the study also found the sound velocity peak at the intermediate density, and it eventually approached the conformal limit. So existence of sound velocity peak itself has been established, but its microscopic nature has not been fully understood. So that's the topic I want to discuss in the following rest of the discussion. Okay, but let me briefly give some orientation. So how a sound velocity should look like in purely nucleonic description or purely quark matter description. Okay, so to calculate the sound velocity, so first we have to know how pressure looks like. And it is intuitively easy to start with energy density at a given number density, because this is most intuitive. Okay, so we first fix a particle number and then consider the energy. So that's rather easy to imagine. And when we want to convert this information into the language of pressure, so this expression formula is useful. So in order to estimate the pressure, so what we should look at is the energy density per particle. Okay, so we look at the average energy of a particle by dividing energy density by number density. Then next we look at how this energy per particle change with density. Okay, so if this energy per particle is just constant, then pressure is zero. For example, let us first consider the massive limit of a particle. Okay, heavy particle system. The energy density is dominated by mass energy density, the mass times number density, plus correction from kinetic energy, which is highly suppressed. So we divide it by number density, and then we get the nuclear mass, or the mass of particle, which is constant. And then if you take derivative, pressure becomes zero. Okay, so this is perfectly consistent with our intuition. So if we consider extremely heavy particle, it cannot move much, and then it cannot create pressure. The another characteristic limit is relativistic limit or Maslach limit. In that case, only scale is a number density or Fermi momentum. So NB to 4/3. So divide by NB, we get NB to 1/3. And if you take derivative, we get factor 1/3. So this is so-called a conformal limit. Okay. Okay, so now, let us start. Let us consider a little bit more realistic situation. So first we consider purely nucleonic matter. So here I parameterize energy density in the following way. So energy density is parameterized as, so first term is mass times number density. This is just mass energy, which is very large. We have a correction from kinetic energy, which is suppressed by the mass, heavy mass. And then we also parameterize the interaction through in this form. So B characterize the strength or sign of interaction, and alpha characterize the power of density. Okay, so starting with this parameterization, we divide energy density by number density, take derivative, and then we can get this expression. What is most important is this mass density drops out when we look at the pressure, okay? And the leading term comes from the kinetic energy, which is small. So therefore, the baseline for nuclear matter description is basically equation of state is very soft, okay? Because pressure is small, but the energy density is very large. So of course, this is a discussion based on non-interacting limit. So now I want to change the situation by considering the strong interaction, okay? So in order to avoid a soft equation of state for purely nucleonic description, interaction must play the dominant role. So now, I consider now the opposite limit. So interactions are very important. And now I consider the situation where interaction completely dominates the equation of state. And then all the other term can be dropped out, okay? So if you just keep the interaction term in energy density and the pressure, then we can easily derive the relation between pressure and energy density. So pressure is just alpha minus 1 times energy density. So what is this alpha? Okay. Okay, so before that, so if from this relation, we can easily derive the sound velocity square, which is given by alpha minus 1. Okay. So what is this alpha? So roughly speaking, when alpha equal to 2, that means that describes basically the two-body interaction. Okay. And when alpha equal to 2, then at a very large density, sound velocity asymptotically approach to 1. Okay. So alpha equal to 2. Therefore, when interaction dominate, then this sound velocity square approach to 1 asymptotically. So if instead we assume three-body interaction, dominance of three-body interaction, then we have to substitute alpha equal to 3. Then in asymptotic limit, sound velocity square go beyond the causality bound, and it approach to 2. Okay, and around here, it violates the causality constraint. Therefore, we cannot trust that model. But the main message here is the following. So there are many studies based on nuclear many-body interaction to explain total mass constraint without using quark at all. And for such model, three-body interaction plays very important role. But the drawback is it violates causality constraint at high density. So that is the one problem. And another problem is when three-body interaction is too important, that raises a question about the convergence of interaction. If three-body interactions are more important than two-body interaction, then natural question is whether four-body or five-body interaction or more body interaction become important or not. And of course, it is very difficult to answer. So therefore, there should be some argument, some alternative baseline should be here. So alternative baseline, possible candidate is a baseline based on quark description. So again, here I consider the simplest possible model which I can imagine. So that is just a free quark gas and with no mass. Then in this situation, the equation of state is just conformal type equation state. So pressure is given by 1/3 of epsilon. And here we have some normalization constant, which adjusts where matter, at which density quark matter should appear. So that is a normalization constant, which we always have to discuss. But this normalization constant, although this is not difficult to estimate, actually it plays a dramatic role. So when this so-called bug constant is very small, okay, is large, okay, when this bug constant is taken to be very large value, then this reduces the pressure and increase energy density. Therefore, large bug constant leads to very soft equation state. On the other hand, if we choose soft enough bug constant, then equation state can be very stiff. Okay. And in fact, if you take sufficiently small bug constant, actually you can produce whatever mass for the neutron star. For sufficiently small bug constant, the mass can easily exceed the two-solar mass constraint. The essence here is, so basically, if we consider relativistic quark, okay, that kinetic energy is large, and it can potentially produce very stiff equation state. So this fits to our intuition. So relativistic particle can create a larger pressure. And it is worth mentioning that so quark kinetic energy is, roughly speaking, the factor 10 larger than the nuclear kinetic energy, and pressure is typically 10 times larger. The reason is, so when quarks look at quark kinetic energy, we have kinetic energy, and the factor NC appear in the numerator. So we have NC different quark that just keep increasing the pressure by increasing the number of color. On the other hand, the situation is quite different for nucleon description. The factor NC appear in the mass of nucleon, and therefore it appear in the denominator of the nucleon kinetic energy. So since quark kinetic energy has factor NC and nucleon kinetic energy has factor 1/NC, therefore difference in kinetic energy is factor NC square, which is the order of 10. So if we somehow could generate a matter in which quark directly contribute to thermodynamics, in that case, the equation state becomes naturally stiffer. So it can be a good starting point, and this will be the essence of the following discussion. Okay, please. Yeah, please.
Yeah, sorry, I didn't follow this discussion. So what happens to PF that is independent of NC?
PF is, PF directly related to the number density.
Yeah, but
So,
the number
PF
density, mu for nuclear quarks and mu for nucleus are different, right?
If you fix baryon density, okay, and if you look at the density of, let's say, red quark, okay, so that density is the same because each baryon contains a single color quark, okay, and Fermi momentum is directly given by the number density. So this PF and this PF is the same PF. If you estimate Fermi momentum from the density. But at least they are the same order in naive argument.
Okay.
Yeah, so this is not chemical potential, but Fermi momentum, which is directly related to the number density. So PF cube coincides with number density. Okay. And the baryon density and quark density are equal. Quark density for a given color is equal because single baryon contains one quark for a given color. Okay. So if that density is the same, and if we use that density to derive the Fermi momentum, then the value of Fermi momentum are just equal.
Okay.
Okay. Yeah. Yeah, please.
Hi, Toru. So what is the dispersion relation for a particle near the Fermi sphere?
Oh, dispersion. Here I just assume free quark. So the
Linear.
So for this is just for comparison. I just consider a non-relativistic approximation.
So it's a large, you're assuming large quark mass.
Here, yes.
So quark mass much larger than the Fermi
Fermi moment.
energy.
So this relatively low density regime. So
Okay.
let's say, this is just for comparison. Of course, quark mass can change, but here just to how to say, for comparison, I choose the same constant quark mass for neutron description and quark description, and just focus on the this factor.
Right. Thank you.
So this is radically simplified description. So please don't take it too seriously. Only point is for quark description, factor NC appear in the numerator. Okay, and for neutron description, factor NC appear in the denominator. So this is a big difference. Okay. So I mentioned briefly. So this normalization constant is very, very important. And so actually, the importance of a bug constant, in my opinion, highly this importance is highly underestimated in our community. But as I said, so the choice of bug constant totally changed the scenario. Okay, so typically, in more realistic situations, so here I just consider purely quark matter without talking about hadronic matter at low density. But perhaps a more realistic description is we have hadronic matter at low density, but quark matter at high density. And we want to discuss some connection. So that is so-called hybrid model. And perhaps that is more realistic compared to the purely quark matter. But there is always some confusion point. So when we prepare the hybrid equation state, so we prepare two different models. At low density, we use hadronic model, and at high density, we have a purely quark matter model. And then we just try to patch these two models, and then try to describe the phase transition. But there is a serious problem. So if you use two different independent models, then we don't know what is a normalization for equation state. So if you combine two different models, the relative normalization is always ambiguous, is subtle. For example, so let us consider the Dirac sea. So if you use a baryonic model, then Dirac sea is made of a nucleon. And for quark model, we have a quark Dirac sea. But it is very difficult to compare the contribution from Dirac sea for two different models. Okay, so we basically don't know how to relate to different Dirac sea energy. So actually, this is a source of confusion. And this gives us uncertainty about the normalization of energy. But so this is very important question, because depending on our normalization of equation state, so we can create two possible scenarios. So if this normalization constant or bug constant is very large, then quark matter EOS is very soft. And this choice is typically used for the description of the model with first order phase transition. We have hadronic model, rapid first order phase transition from hadronic matter to soft quark matter EOS. Okay, and in that case, quark matter EOS must be regarded as soft because of large bug constant. But if we choose a smaller bug constant, so we don't know how hadronic matter change into quark matter from conventional language. But anyway, we can create a stiff quark matter. Okay. But so everything is controlled by this choice of bug constant, and we don't like it. So therefore, in the following discussion, so I will keep track of quark degrees of freedom all the way from nuclear to quark matter region. And in that way, we can avoid the question about normalization constant. And of course, such kind of description is very difficult theoretically. And in fact, my description is rather awkward. But instead, it gives a very transparent picture about the relation between hadronic matter and quark matter. Okay, so now, so large time already passed, but let me give the essential point. So So first I consider so I will consider some duality between hadronic description and the quark momentum description at the level of occupation probability. So this is the thumb rule. So there are three important functions. The first function, important function, gives the information about quark momentum distribution inside of a single baryon. Okay. So in principle, we can solve the three-body problem for a single baryon and calculate wave function and calculate a momentum distribution. Okay, that information is here. It depends on the quark momentum and also baryon momentum. And another important information is how a baryon occupies state in dense matter. For example, if we consider ideal baryon gas, in that model, the baryon occupies state from zero momentum to Fermi momentum with probability 1. Okay, so this is the usual ideal gas. And if we integrate over this phase space, we can calculate number density. Okay, so now from combining the this baryon occupation probability and information about quark momentum distribution in a single baryon, so we can sum up each baryon contribution or quark contribution from each baryon, and you can sum up. Then we can derive information about occupation probability of quark states. Okay, so how quark states are occupied can be calculated in this way. Then this is example. So if we consider dilute regime and ideal baryon gas, then basically the finding is the following. So quark occupation probability has so this function basically has a shape almost same as a vacuum momentum distribution function, but its height simply a scale-like number density. Okay, so this can be derived from this simple thumb rule. Okay, so now to make a complete computation, so we will consider some idealized model. So that was recently developed with Yuki Fujimoto and Larry McLellan. So our simplification is the following. So first, to avoid any detailed discussion about the interaction, so we all neglect interaction except the force responsible for confinement. So confining force is expressed by assuming a quark distribution in a baryon is like this. So this so distribution has some width, which is order lambda QCD, and this is related to the inverse baryon mass, baryon radius. So if we take a large lambda, that corresponds to the point particle limit. But if you consider smaller lambda, it means we are considering the rather loosely bound baryon. Okay. So this momentum distribution comes from the fact that the quarks are trapped within the small spatial region. Okay. So if we consider more compact region, then this momentum distribution has a wider width. But if we consider loosely bound nucleon, in that case, quark distribution has a spread like in plane wave, and momentum is more concentrated on into the low momentum domain. Okay, so that is our expression for confining force. Okay, and next, so another assumption simplification is we assume quark distribution in a baryon remains the same from, let's say, 2 to 10 times nuclear saturation density. That means the message is confinement is assumed to such density. The third special simplification or assumption is, so if we use some special sort of quark distribution, then this model can change into solvable model. So if we use, so there are of course several freedom to choose this wave function or momentum distribution. But if we choose this momentum distribution to be the inverse of this operator, then this wave function, if you apply this operator L to this wave function, we get delta function. Okay. So this is our thumb rule, which gives the information which derive a quark distribution as output from this formula, and FB is the input. But if we use this special moment distribution for a quark, then this sum rule can be solved explicitly, and baryon distribution can be derived as an output as a local moment, a function of local momentum. So if we use this assumption, we can freely change the language. So in some situation, we can use the language of quark, but in some situation, it is better to use the baryon distribution. But we can freely switch the language. And this is especially useful, especially when we discuss the domain where degrees of freedom are not clear-cut. We are looking at the domain where degrees of freedom might be baryon or might be quark. It is sort of question. But if we have two languages, we can look at both physics at the same time. Okay, so this is our Hamiltonian or energy density as a functional of baryon distribution. Okay, so this is our Hamiltonian. And what we have to do is just minimize this energy density. So this is like a Fermi-Likit theory. Okay, so FB is a functional, as energy density is a functional of this distribution function FB. Okay, so this is just a variational problem. So we impose the fixed number density, fixed number constraint by introducing Lagrange multiplier. And but the energy baryon is given by just experimental mass plus momentum, and we can just optimize this energy density with constraint. Okay, then so we get EB minus lambda B. Lambda B is Lagrange multiplier, and this equation is given by momentum. So there are several domains. So if we look at very large momentum, then this EB is larger than the chemical potential. And in that case, the right-hand side is positive. Okay, so therefore slope is positive. So minimum solution can be found at FB equal to 0. Okay, so large momentum, that occupation probability is just 0. Okay, high momentum particle should not exist in the ground state. On the other hand, if you look at the low momentum domain, then EB can be smaller than the chemical potential. And in that case, in usual model, so this slope is just negative, and the minimum solution, optimized solution, is FB equal to 1. Okay, so this is we have just a step function. Occupation probability is 1 at low momentum and drop to 0 at high momentum. So that is usual ideal baryon gas description. But the situation becomes different when we consider the quark substructure constraint. So as I said, so this FB, okay, is now combined with quark substructure information. Okay, and there is some non-trivial constraint. So at the high density, so quark substructure constraint enter, and actually the FB, optimized FB, cannot reach 1. But before reaching the maximum value, the constraint from the quark distribution enter. So occupation probability of quark state must be less than 1 because it is probability because of the quark Pauli principle. And if you include this constraint, then baryon distribution cannot reach 1, but it must be stopped somewhere. Okay, so this region is forbidden. And this is the new non-trivial structure of the problem. Okay, so in dilute regime, so we have ideal baryon gas, and the quark distribution, corresponding quark distribution in many body system is just like this. And as we increase density more and more, quark distribution simply grows up in the vertical direction. But you can easily imagine, so the evolution must be terminated somewhere, because this distribution cannot go beyond the maximum value 1. Okay, so at some critical density, so this quark occupation probability hits the maximum value 1, and we call this phenomenon quark saturation. Okay, and after quark saturation, so we cannot keep going, just keep increasing a baryon distribution like this. If we keep going in this way, then quark distribution just violates the quark Pauli principle. So therefore, something dramatic happens after this density. So as we increase density further, so quark states are fully saturated, and quark distribution must evolve into this direction. What is due to quark distribution is baryon distribution like this. Sorry, any question? Okay. And as I said, from this relation, okay, in this solvable model, so if you give a quark distribution, and then we multiply this operator, and then we can calculate baryon distribution. Okay, so that kind of derivation is possible. So this we can imagine. Okay, so we have a saturated quark state and some tail near the Fermi surface. And by applying the operator L, you can calculate baryon distribution. And now we found the following. For the saturated region, okay, so baryon solution cannot reach the maximum value 1, but it must be stopped. And the theory predict it is order 1 over n3 cube. And the region where quark states are not fully saturated, so we can choose ordinary solution. Therefore, the occupation probability is just can reach 1. Okay, so this is what we have for the baryon in the case where quark states are saturated at low momentum. Okay, so this description gives something very important for the very important implication for equation state. So look at here. So low density, low momentum states are underoccupied, but high momentum states are more occupied. Okay, so in that sense, so baryons are more relativistic compared to the ordinary description. So we have to push baryon into high momentum to avoid quark parity principle, violation of quark parity principle. And therefore, baryons should be relativistic. And if there are relativistic baryon, equation state should be stiff. Okay. And this sort of structure is inevitable after quark Fermi C is formed. Okay, so this is the schematic picture, what happened. So this is pressure versus energy density. So if we just neglect the quark substructure, then equation state of baryon is very soft. Okay, but we cannot keep going in this way because at some point quark saturation sets in. So therefore, there must be inevitable stiffening somewhere around 2 to 5 times saturation density. And then the equation of state change from nucleonic type to the quark matter type. Okay. So actually, this saturation effect is the origin of the sound velocity rapid stiffening and the origin of sound velocity peak. And so if we just consider our ideal model, then actually there is some artifact. So equation of state just make infinite speed of sound because of this jump is rather discontinuous. But of course, this is just due to the oversimplification of our modeling. And by putting interaction, this discontinuous structure should be smoothed out. Okay. So interaction should regulate this rapid enhancement into a more realistic value. And here I emphasize this stiffening is exactly opposite to the conventional first order phase transition. In the conventional first order phase transition, pressure is constant, but energy density jump. Here, the situation is opposite. So energy density is continuous, but the pressure rapidly grows. Okay. So therefore, this sort of transition is exactly opposite to the conventional first order phase transition. And this is a new finding, which comes from the composite nature of baryon. Okay, the last topic, sorry. So let me briefly mention the hyperon puzzle by applying the previous model. The hyperon puzzle can be defined as follows. So this is a mass radius curve. So this is for purely nucleonic matter. And when hyperon appears somewhere, then it drastically changes the structure of equation state. So when hyperon or delta excitation appear, so what happens? At the threshold, So it adds a large energy to the system, okay? Because it is fast to begin with a non-relativistic regime. So it adds a large energy, but it cannot add a large pressure. Therefore, equation of state must be very soft, okay? And also, hyperon. There are many types of hyperon, okay? So sigma, 3 species of sigma, or 2 species of xi, and lambda. And if we consider decouplet, we have even more particle, and every appearance of particle a softening equation of state. So this is a serious problem. And to avoid this problem, often used approach is just to introduce a strong strong repulsion between nucleon and hyperon, or hyperon-hyperon, or hyperon-nucleon-nucleon 3-body interaction. So by putting more and more interaction, basically such kind of effect can prevent the appearance of a hyperon. And in that way, the model is just like a nucleonic model. But again, this sort of argument does not fully solve the problem conceptually, because it always raises another question: why a repulsive force continuously should appear? Okay, so what is the origin of such repulsion, etc., must be answered. So alternative idea to solve this problem to consider the quark substructure effect or quark saturation effect. So there are several advantages over the conventional nucleonic model. So first, our repulsion is basically comes from the statistical repulsion, which is protected by Pauli principle. And another advantage is it can guarantee the repulsive nature at the high density matter, okay? Because Pauli principle becomes more and more important at higher density. And finally, our model is not just a hybrid model, but describe a single situation using 2 different languages. So therefore, there are no double counting. And there are no double counting from a different hyperon. Okay, so that's important to avoid the over counting of the strange quark. And so this is the extension of the previous model to the multi-flavor case. So this is the quark distribution for up and down and the strange quark. And right hand side, we consider all possible baryon species, so proton, neutron, sigma, etc., and add all contribution from each baryon with some factor, probability factor. So the important point is, so when we consider proton, neutron, lambda, sigma, etc., okay, then all of them contribute to the up quark and down quark and strange quark. So for example, if the system contains a lot of proton and neutron, then those occupy or dominate U quark and D quark states already. Therefore, if you try to add lambda hyperon, for example, that contains UDF, so there is no room to enter. Okay. Similarly, sigma hyperon cannot easily enter the system because all of these states, the U quark and down quark states are already occupied by proton, neutron, etc., etc. So hyperon cannot easily enter. So even if we neglect the interaction between hyperon or nucleon, just considering this quark substructure constraint, we can generate non-trivial flavor correlation among different baryons. And this is just some result. So this is a figure about strangeness fraction. So this is baryon chemical potential, and this is charge chemical potential. Okay. So if we consider lambda equal to infinity, that corresponds to the point particle limit. So okay, there is no quark substructure effect in this limit. In that case, strangeness appear around here. Okay, about 1.1 or 1.2 GB. Okay. But if we consider quark substructure constraint by taking lambda equal to 0.3 GB, that is the typical size, then the hyperon is highly suppressed or excluded from the system because of the saturation constraint. So if you look at the occupation probability of U and D quark state at the 0 momentum, then already around here, the first down quark states are fully saturated by neutron and also proton. And after U quark and D quark saturate the low momentum states. then the hyperons are excluded, and then the threshold for hyperon is highly shifted to high momentum. So this is a statistical repulsion on hyperon. Okay. So this is my last slide. Sorry for extending my talk, but let me summarize my talk. So the first important point is recent neutron star observation seem to suggest the equation of state of QCD should be soft to stiff type. And to describe such a soft to stiff equation of state, the crossover picture should be a good baseline. And so, although I didn't emphasize much, so quark saturation effect likely occur around 1 to 3 times saturation density, slightly above nuclear saturation density, if we use the rather typical or conservative, even if we use conservative value for the quark momentum distribution inside of a single baryon. And it produces a statistical repulsion and make baryons relativistic even at such low density. And of course, a quantitative estimate of this saturation, onset density of saturation, of course, depends on our estimate of quark wave function of hadron in medium. But if quark distribution, if quark momentum become, if the baryons, for example, become bigger in momentum, in medium, then quark distribution can concentrate on the low momentum region, and that make the occurrence of saturation earlier. Okay, and so the location of Sandberg's peak is actually correlated to the substructure effect and quark saturation effect. And this gives a new context on the relationship between neutron star equation state and hadron spectroscopy. And this link is now being built. And another important question, which I haven't addressed, is so I consider for a long time that how quark exchange and appearance of quark matter are related. So when I consider the nucleon-nucleon interaction, there are quark exchange. Okay, and as we increase the density, somehow that quark becomes a real particle in the sense that it starts to directly contribute to the pressure. So how that transition can be described is a future problem. And with this, I conclude my talk, and thank you very much for listening.
Thank you so much, Toru, for the nice talk. Any questions from the Zoom audience? Okay, if not, any questions from the audience in this room?
Yeah, this might be a little technical, but can we go to around slide 13, 14?
Page, sorry.
Page, 13, 14, around that, precisely.
This one?
No, way back, like 13, 1, 3, 1, 3, 1, 4.
Sorry, sound is somehow resonating, and it is difficult to listen.
Could you go to your slide number 13?
Number 13. 13.
Yes, 1, 3.
Okay, 1, 3. Okay. Okay, this one? Different, right?
No, maybe go ahead a few more slides.
Previous one? This direction one?
Go ahead.
Yeah. Go ahead if you could, like maybe slide 13, 14, 15, and so on. 15,
okay.
So they have the mass radius relations and then quark matter in between. Go ahead.
Mass radius relation.
Yes, that one. Yeah, this is fine. So after your transition to quark matter, your equation of state seems to be still quite hard, right? You can still get neutron stars of mass around 2 quite easily. Is this because you're using a smaller back constant, or have you put in repulsion in the quark matter sector?
Sorry, which model are you talking about?
So let's say your gray curve, when you have a transition to quark matter, usually what I remember is that if you have weakly interacting quark matter with usual back constant, then these equation of state TD, just the mass stagnates at a very small value, like 1.5, but soon after the transition. So, but in this case, it seems to be going up quite a bit. So, is it because you put in some repulsion in the quark matter, or is it because of the low back constant? That's what I was trying to understand.
Okay, yeah, actually, it's very difficult to hear, but you are asking whether this behavior comes from the choice of bulk constant or repulsion force. Am I right?
Okay, maybe.
Yes. Yeah, it's difficult.
So I'm trying to ask in the quark matter equation of state, when you have a transition to quark matter.
Yeah.
Yeah, here.
Okay, here.
So how did you get the quark matter equation of state to be quite stiff?
How to get?
Yeah. Usually quite soft, typically. That's what I.
Yeah, but yeah, it depends. Okay, first of all, it depends on the choice of bulk constant, for example.
Sure.
Okay, and so actually there is no rigorous reason why quark matter should be soft.
Okay.
So of course, yeah, but yeah, conventional model historically, so people use soft quark matter equation of state to construct hybrid model.
Yes. Yeah.
But that is for the purpose to create hybrid model with first order phase transition. But if we don't try to use first order phase transition, then actually there is no reason why quark matter equation of state should be soft. Okay.
Okay. So you're saying
That's
it's
my main message in the first part. Yeah. So quark matter can be quite stiff. So I gave this argument. So if we, for example, use small bulk constant, then equation of state can lead to the maximum like this. Okay, so there is no interaction, but just a kinetic energy. Okay, and that argument alone can give a very large mass. Okay, so no interaction is used, but just the kinetic energy. Okay, so that can produce very large mass. Okay.
Okay. Thanks.
Yeah. Yeah. So actually, this is very important in my opinion. Yeah, so therefore, yeah, if even without interaction, it can create a stiff equation of state. So why not using quark matter as our baseline? Yeah, that's my statement or my question. Then whether we should use quark matter or hadronic matter depends on the relative relation, which I discussed here. Okay, and the conventionally people try to describe the model of the first order phase transition. So people implicitly choose the soft quark matter equation state. Otherwise, we cannot describe first order phase transition. Okay, so that's the reason why actually I myself was confused when I studied the quark matter and hybrid model, because many people told me a quark matter equation state should be soft. But when I studied the bug model, actually quark matter can be quite stiff. And the reason why people regard a quark matter to be soft is people mainly consider this sort of model. So there is some bias. So there should be first order phase transition from hadronic matter to quark matter. And in that bias, the quark matter, the hybrid model must take this form. And here we must have the soft quark matter. But if we don't stick to the model of first order phase transition, then there is no reason why quark matter should be soft. Okay. And as I said, so quark matter actually can be quite stiff, even without a detailed description of the interaction. That's the point, because if your theory is dominated by interaction, then something is wrong. So interaction should be treated as small correction if we choose proper degrees of freedom. If interaction plays too important role, then we are choosing long degrees of freedom, typically.
Any further questions? Okay, if not, let's thank Toru again.
Yeah, thank you so much, and I'm sorry for extending.
No problem. Thank you so much for the very nice talk, Toru.
Yeah, thank you so much.
For keeping you so late. Thank you.
All right.